With example 2, we're going to be a little bit more closer to what happens in neural network. We have a 3-layer neural network, well, some layers neural network, we don't need to go beyond 2. And it's a very simple neural network, it's just silly. So we have one weight and one bias for every layer. So wj minus 2, bj minus 2, we have the output, wj, bj, and then whatever. And then from input to the whole output here. So you can write down the dynamics here as f, the final output at the last layer, gonna be 1 minus activation of that layer, aj. And then you can define recursively aj equal to sigma, nonlinearity of zj, the output. So you're going to have this Cj and then path it through some nonlinearity and then say that this is your final output. And then Zj minus 1 is Wj Aj minus 1 plus Bj, okay? And you can do that for all the J, and then the final layer going to be F. Well, the final layer going to be Y, and then this is the final penalty, the actual objective function. So for that, what you can do is now the same trick as example 1. So you can now write down the computational graph here, starting from the output perhaps, because this is a recursive from the output. So you can start from the output F and then say F is, can be evaluated if you have Y and AJ. How? Through this very simple function anyway. And then Aj is a function of Zj only, and Zj is a function of these three, and then you can do that for all the layers. So Aj minus 1 is a function of Zj minus 1 and all the way down, okay? And this is just a computation that you need to have in this very simple neural network. Now, what is the role of backpropagation here, as you have seen? So you're going to start at, well, you can, what you can do is that you can find the gradient of this guy with respect to all the nodes here with just going one path from F all the way down. You can do that very easily, right? You just need to use the chain rule. For example, if you want to find the gradient of this guy with respect to that guy, what is it? It's just a gradient of this guy with respect to that node to that node, and this node to that node, which is essentially this guy. So actually a product of these gradients that you have seen in example 1. So this gradient should be gradient of F with respect to Aj, right? This guy should be gradient of Aj with respect to Zj, and then this guy should be gradient of Zj with respect to Wj. If you want to go from F to Wj minus 1, which is another parameter, the only thing that you're going to need is product of this guy, this guy, this guy, this guy, and that guy. That's it. And then you have stored everything. How you would store, you go one path from the input to the output. It means that for one sample, for example, you will find all these guys, okay? And then you have essentially all the information that you need. So what does it mean? It means that if you find this guy, what is this? This is, for this objective function, this is 2 times that guy, right? So minus 2 times y minus aj, okay? Well, yep, or 2aj minus y. Okay, so do you have that? If you go one path through the network, one forward path, yes, you do. Why? Because if you go one path through the network, you can compute all these parameters anyway, right? You will have all these parameters stored in your network. Just imagine that this is all the parameters that you have in your cache of your computation. So you have aj, you have y, so you can compute 2aj minus y. So one pass forward gives you all the information that you're going to need to compute this. What is this guy? This is sigma bar of zj, the gradients of this nonlinearity. What is this? This is just aj minus 1. Why? Because the gradient of zj with respect to aj, with respect to wj is aj minus 1. And then you already have that if you go one pass to the network. So what does it mean? It means that you can go one pass for every sample. You can have one pass from the inputs all the way to the f. You will store all these parameters. This is not efficient, by the way, but just saying that you can do that. You store all the weights, and then now you can use backpropagation to find all the gradients, so gradient of f with respect to all those w's very efficiently. In this very simple example, where you don't have multi-layers, you have multi-layers, but then you don't have multi-neurons here. But then you can imagine that adding several neurons here wouldn't really complicate anything so much. So it's just adding some more indices to that computational graph. So nothing fundamentally is different in that case. Instead of having just, in that case, we have a tree. In that case, instead of having a tree, we have a little bit more complicated graph. Nothing is fundamentally different in that case. So just couple more indices and a little bit more heavier computation, but completely doable. And then you have that everything for just one sample. So this is f, is actually f of I, to be more precise, f with respect to objective with respect to one sample. And then we have seen in backpropagation that the efficiency is that you can find the gradient of the objective, one objective with respect to all the inputs. But then what if you have 10 objectives? Then you're gonna need 10 times of this guy, right? So it essentially means that if you have a mini batch, then you have 10 of those Fi, and then you're gonna need tens of those rounds of backpropagation to find the gradients. It's still much more efficient if you have 10 objective functions and summation of those 10 objective functions and 60 million parameters. This is essentially what you would have compared to the forward mode where you can find the gradient with respect to all those 10 objective function at once, but then you need to do that 60 million times. Okay, so that was essentially a sense of backpropagation, and then you can just generalize that to a full deep neural network with many different architects of convolutional network, recurrent networks. So all of them are almost the same. What you need is to find the computational graph and find the gradients on the edges and just do the product of every path, find all the paths within one target node, which is a parameter wj, and one source node, which is your objective function, and then you can go all the way through different paths to find the gradient with respect to that parameter. So really easy to code. And it's, by the way, available in all the libraries. Some more issues on training deep neural network. The first one is, as we have seen in the first recap slide, is that the curvature of f, unfortunately, whenever the dimension of that optimization problem, so the cardinality of that set W, is high, then the curvature of f is not even across all dimensions. So instead of having something like that, which is a small L over mu, you have something like that. Again, L is a smoothness and mu is a strong convexity. In general, doesn't have to be convex, but the whole idea would be applied there as well. So the geometry is something like that usually. So what you should do in this case? Any idea? We should do preconditioning, right? But then what happens in neural network, let's assume that we want to use this guy here. So we want to run wk plus 1 equal to wk minus alpha k gradients. For sake of simplicity, assume that this alpha step size is constant for sake of simplicity. Well, it just doesn't have to be. Let's alpha k minus alpha k gradients, okay? And then we use backpropagation to find these gradients with respect to all the parameters, all the inputs I, or all the samples I, or a subset of those samples, call it mini batch. But then what happens is that it really doesn't respect the geometry of the optimization. So then you may need to somehow precondition this gradient, so call it minus alpha gradient. You're going to precondition that with the Hessian information perhaps, but they could be too expensive. So there are lots of approaches like that anyway that can hugely reduce the convergence time for training this very large scale optimization problem. But what we can do is to take an alternative view. So the thing that is important here is not the gradient itself, it's the product of gradient and alpha k, okay? So if it just happened that instead of playing with the gradients, trying to precondition that, what we can do is that we can play with alpha k. Why not doing that? But the usual way that alpha k is designed, and this is just one approach, by no means this is the best approach, for sure not. But then this is a very efficient approach anyway. So the usual way that you have seen so far is don't differentiate individual dimensions. For all the dimensions, use alpha k. That's why you have WK. We don't have any index for, the only index is for iterations. There is no index for individual dimensions, right? So WK plus 1, all the dimensions, that vector is previous vector minus 1 constant for all the vectors, for all the elements in the vector, times gradient. So the only thing that somehow defines how much we should progress in this dimension and how much we should progress in that dimension is only gradient, okay? So in this case, what happens is that the gradient with respect to this dimension may be small. So in that case, we're gonna have these oscillations. Okay. Because we don't have so much progress in this dimension due to the small gradient, whereas we can have a lot of progress in this dimension. Progress means change in this direction. So that's why that we have high gradient with respect to that dimension, both of them with the same alpha. So what you can do is, instead of playing with gradient, you can play with alpha, okay? So different alpha for different parameters. So this is feasible, but then again, what we have seen is that the alpha k usually, at least so far, they have been designed either a priori, usually, well, actually always a priori, either constant or setting some diminishing with some property. You have seen that. And then definitely those alpha k were independent of this f of wk, so the local geometry. But then what we can do, again, is just to play with that, but then you can just imagine how it would look like. It's like, instead of having a preconditioning matrix that will somehow precondition gradient, you're going to approximate that with, so instead of, let's see, instead of having let's say, let's put bk as the preconditioning matrix, gradient of f at point wk, and then you had usually one alpha k here, and constant alpha k for that specific iteration was a constant for all the dimensions. So this bk would somehow precondition that. So what you can do is that just remove this guy. So say bk is equal to I. Okay, so remove this guy, but then instead of having alpha k, put a diagonal matrix here. Okay, well, actually that doesn't have to be there. Yeah, diagonal matrix here, where you have alpha k1, alpha k2, all the way to alpha k, the last dimension. Let's say this is D. Okay, so it's like an approximation of that preconditioning matrix that you have, kind of first order approximation. Well, in general, doesn't have the first order. But it's like a diagonal approximation of this bk. So it may not be as good as if you had bk, but it could be computationally way more efficient to find this compared to that bk. What should be the preconditioning matrix? And that's actually a great deal in optimization. Why? Because now you can have some efficient algorithms that somehow precondition the whole function. And the whole role, and definitely you can converge much faster in this case if you properly choose these. So emphasize on different coordinates or different parameters. But this is not the whole reason, actually. Another reason, which seems to be actually even more important, is something like that. So what you do have is, in general, you have wk plus 1, wk minus alpha k. For sake of simplicity, I assume that this is just alpha, again, constant. Or, yep, alpha gradient of f. Assume that this is, again, diminishing alpha k. Okay, just for sake of arguments. What would happen is that, and just assume that this gradient up to the first 1,000 iterations, many iterations, is very small with respect to some of those coordinates. Okay, it just happens to be like that. So you don't have so much information in the first 1,000 iterations. You don't have so much information in terms of gradient with respect to a couple of those parameters. But then what happens is that you're going to have update with respect to those non-zero parameters of the gradient. So this is a vector, gradient of f of wk, entry 1 of that with respect to parameter 1, all the way with respect to parameter d. Okay? In the first 1,000 iterations, these guys are high values, but these guys are very small values. But after 1,000 iterations, these guys are going to be high values. Okay? But what happens is that these guys will be somehow multiply by this alpha k, they will be really damped after 1,000 iterations. Whereas this dampening is really good for these guys because we had a lot of good progress here, and then we are very close to the optimal solution anyway. So this dampening really makes sense for the first part of these parameters, some of those parameters, but not all of those parameters. So this is called a sparse kind of parameter updates where all the parameters, they are not expressed similarly in the optimization. So some of them are expressed more than the others. And this is exactly what would happen here. So in that case, those gradients are usually 0 in many of those iterations, but then non-zero in just a couple of iterations. But then if you treat them the same as some other dimensions like this dimension where you have, well, actually this dimension, where you have a lot of gradients in all the iterations, then that alpha k, whenever you have that information on those sparse parameters, then it's going to be killed by this very small alpha k anyway. So this is actually one more important reason why you should treat them individually. Of course, you can just say that this alpha is a constant, even constant, or diminishing or whatever. It just doesn't matter as long as you do this preconditioning. But then if you don't have this preconditioning, this is the least that you can do. So let me see here. Okay, so one way to do this preconditioning is that, okay, so I can perhaps use this again, is that you can just keep record of these gradients in all the iterations that you have. In the first iteration, second iteration, all the iterations, all the way to iteration t, or iteration k, and then what you can do is just to accumulate the norm of the gradients. So what it does is that if it happens that parameter 1, so coordinate 1, has high values for the gradients in the first 1,000 iterations, okay, then we had actually a lot of good progress in that coordinate, so we can dampen alpha for that coordinate. But then if some of those coordinates are very small in lots of iterations, we didn't have good progress in those coordinates, so we need to increase alpha for them somehow. Either increase alpha or don't decrease alpha at least. This is what you can do. So then keep record of this epsilon is just for the regularity purpose to have 1 over this bk defined. So this is a very small 10 to the power minus 12 or so, very small value, plus a diagonal of this gradient matrix that you have seen here, times the same thing here, transpose. So essentially what it means that it's going to be a diagonal in the diagonal element, and then you're going to just look at the diagonal elements of that matrix, big matrix. This is a D by D matrix, and then you're going to just look at the diagonal elements of this matrix. And the first diagonal element is norm 2 of the first gradient with respect to, at iteration k, with respect to coordinate 1. The norm of the gradient, L2 norm of the gradient with respect to coordinate 2 all the way to coordinate d, okay? So this is actually how big is the magnitude of the gradient at that coordinate at that iteration. And you're going to just sum all those over all those iterations, okay? Cool. And that's it, essentially. So this is, as I said, so this is an accumulation of all the gradients over all the iterations of that specific coordinate. Do we have an update here? No, I didn't mention. But then this is actually bk. So what you would do is that instead of having alpha, you're going to use this bk inverse, or with some small alpha. So you're gonna run this iterative algorithm again. Set alpha equal to alpha k equal to alpha some constant, and then multiply by bk inverse. Okay, but then the way that bk has been defined is it would be just a diagonal matrix at the end of the day. And then since the diagonal matrix, as I've mentioned, is like an approximation of the actual preconditioner matrix that you should have, but then that works more than fine actually. Okay, and then this algorithm called ADGRAD, which is very famous, and it really does make sense. As I've mentioned, if you have some different kind of parameters. Some parameters are very frequent, namely their gradients are very high in many iterations, whereas some of those other parameters, their gradients are not that much high. So if you again recall this optimization landscape, you can see that in one coordinate the gradients are very high, but the other coordinates gradients are very small. Okay, so then you would create them differently. And then it's going to boost infrequent or rarely occurring parameters. Actually, it won't boost them, but it won't damp them as well. Okay. Another good thing is that you really don't, you are much more relaxed in hyperparameter tuning. So that alpha, perhaps you have seen that your iterative algorithms in your computer assignments, that your iterative algorithm is a function of that step size, and then it might be really challenging in some cases to tune that alpha, what should be that alpha. But then in that case, it's a very easy choice, because almost independent of what is the value of alpha, after a couple of iterations, the main component that affect how you should update individual coordinates is like, so again, it's not coordinate descent, by the way. It's still gradient descent, but then you're going to have different step size and different coordinates. But then the main component is going to be this guy, not the alpha product b minus 1, bk minus 1. So that's going to affect everything at it. So then we have a much easier hyperparameter tuning here, which is very nice. But then what is the problem? Here you can imagine the problem is just vanishing a step size. Again, what's the step size? In this case, alpha bk inverse, okay? But what is the problem is just we are just accumulating over all previous iterations. And if it just happens that you need thousands of iterations, here you're accumulating over 1,000 iterations. And it just doesn't matter if that specific coordinate is sparse or not. Again, coordinate being sparse means that these gradients are small for some of those coordinates. It's just the aggregation of thousands of those small values. It's going to be a high value anyway after some iterations, some high number of iterations. Then you're going to have a vanishing step size. So then you can have some very simple heuristic algorithms here. So one of them is like fixing this to W previous iterations or K previous iterations instead of aggregating over all. The other one, which seems a bit more reasonable, is using exponentially decaying average. So instead of summing up everything here, what is the meaning of summing up? The meaning of summing up is, I'm calling this guy, this summation B. So bk in this case is bk minus 1 plus the new gradients, right? Gradient of f to power 2, well, norm of this guy. This is the meaning of that at point k. That should be gradient of fwk. This exponential decaying says that instead of that, use bk, I don't know, gamma bk minus 1 plus gradient of fwk, norm to 2. So in that case, you're going to exponentially decay after some iterations the previous one. It's still you're summing up over everything, but then exponentially giving less emphasis on the very old values that you had. Okay, you can just write it down and then see that the meaning here is that you would have this gamma should be smaller than 1 anyway. So that gamma to power k gradient at first iteration, that gamma to power k minus 1 gradient at the second iteration. So that's the meaning of exponentially decaying average. And this algorithm calls RMSprop, very famous one, used almost in all neural networks. Either this guy or Adam, which seems to be a bit better than that. And Adam is essentially, again, the same idea. So again, just remember that all of them are like an approximations to that preconditioning matrix. We start from just accumulating all the gradients and then seeing that this may vanish 1 over that guy, so it may grow a lot. Then we go with exponential decaying, and then you can see it's actually not that much hard to see that there is a bias here, and then you can just normalize that bias. So you can add 2 terms. So instead of just easily working with bk, you can add bk minus something divided by something, okay? And that something in the numerator and that something in the denominator is a famous normalization that you can do, a bias correction term for the first and second order moments. So bk minus something divided by something, and that something in the denominator is the variance. And then you can recover something called adaptive momentum estimation, ADAM algorithm. I would suggest you to look at that, but then the whole idea essentially is the same, but just adding some term to this. Okay. So, any questions so far? Okay, cool. In this slide, we're talking about overparameterization. So we can see in some other slides that the number of parameters could be really huge. So this is what you would do usually. So usually you wouldn't really optimize over the number of neurons or the number of layers. You just randomly, with somehow gut feeling, says that, okay, a deep neural network of this number of neurons and this size is just enough for this task, and then train and then see the training performance. So this is what you would usually do, and then see if you are happy with that training performance or not. But then what happens is that usually that network is really over-parameterized, that optimization problem. Again, on the positive side, you have a very good expressiveness power, but it's really hard to optimize that. The cost of adding more parameters is, first, statistically, it would be much easier to overfit to that. But then more importantly, algorithmically, it's going to complicate the whole optimization problem a lot. If you just randomly add some more weights there, you shouldn't really do that. But then the way to somehow compensate for that, there are many different ways. From a statistical learning theory, we can use something like data augmentation. So either go and then add some more data to somehow address that overfitting problem, to use perhaps that expressiveness power in a good way. Or what you can do if you don't have that data, and this is a very easy one actually. So you can use the existing data that you have, apply some linear transformation to that. So namely, if you have a picture, just rotate that picture, add some noise to that. Well, noise doesn't have to be linear, but usually you can just rotate that picture somehow, and then use that as a new sample to your data set. So then you can augment that data set. The thing is that in that case, you're not changing the statistics so much. You're not changing the statistic of your data set. So that wouldn't be as good as if you add some independent data, some new data, but then you don't have access to new data anyway. So in that case, this is what you can do. The other approach is adding regularization terms. So norm 1, this is, of course, you can add that. The other one is dropout, which what it says that just randomly drop some weights. So make the whole network a bit sparser, but just randomly dropping. So consider a fully connected neural network. So all the weights are there, just randomly drop some of them and then train. So that actually works magically. Essentially, what does it mean? It means that the actual network that you were dealing with was really over-parameterized, so it could really tolerate dropping some of those weights. Anyway, and then the last one is just earliest stop. So what happens is that, and then this earliest stop has nothing to do with this statistical learning, it's more about algorithmic part. So you're gonna be close to somehow the solution, but then the solution that you would end up to, it would be over-parameterization. It would be overfitting, overfitted solution anyway. So we do have this famous curve. I'm not sure if we have covered that, but then we do have these famous curve of the number of iterations, okay, and objective function, and then this is your training converged to at some very huge number of iterations, converged to local minima perhaps, and then you have this for test training. So earliest stop means that don't go all the way here, so as you can minimize and go to a smaller and smaller and smaller value of the objective, so closer and closer and closer to your local minima. Just stop earlier with the hope that that earlier would have a smaller test error. Namely, you don't overfit so much. Okay, so this is the whole meaning of early stop, which works fine anyway. But I would honestly suggest you these two. Of course, you can do the first and then the last one. But then just think about these two and try to understand what is the main difference from optimization perspective between these two. So here in W norm 1, what you would do is you don't really emphasize on any of those weights. You just say that the number of non-zero elements in all those weights, concatenation of all the weights of neural network, it should be small. But then here in dropout, you have a little bit more control on how you should do that and what of those weights are more important than the others. But on the negative side, adding this term would complicate a little bit the computation of the optimization problem. Just a little bit, not so much. How to address this? If you have an objective function plus this guy, how you should address that? You should use soft thresholding, right? We have seen that in some other lectures and homeworks, I guess. So batch normalization. This is another cool idea that magically happened in 2015. So very famous one anyway. So what does it say? It says that what people were doing for the last 2 or 3 decades was just normalizing the input data. And what is the main reason? The main reason is that your data set, let's say, it is about the price of apartments, and the dimensions on what are the inputs. The inputs are like the location in terms of, let's say, X and Y, for example, in whatever with some coordinate. And the other location, the other parameter is the size of the apartments, okay? So these two, the scale of these two are completely different, definitely not at the same scale. So what happens is that if you go back to that computational graph here, for example, sometimes, somewhere, you're gonna have something multiplied by this Wj somewhere, okay? Then that Wj for one parameter is in order of millions, and for the other parameter is in order of 10 to the power minus 12, for example. So what does it mean? It means that unnecessarily, actually wrongly, you don't get the actual gradients, not because that specific feature is not important, but just they are not at the same scale. You need to rescale that anyway. So this is the whole idea. Just to put all the inputs, normalize them to be on the same scale. And then the way that you can do that is that go through all the inputs, find the average and find the variance of that, and then compute inputs minus average divided by variance plus some small epsilon, 10 to the power minus 12 or something like that, just for the sake of computation. So this is the usual way that you can do in the first layer. You would do that usually, so normalization of the inputs. But then in 2015, people said, so why not doing that in all the layers? Which does make sense. Why? Because again, if we go back here, we could have that problem in the very low part of this computational graph, but then we can have exactly the same problem in all these layers, right? Again, those guys may not be at the same scale, so why not doing that at every layer? Of course we can do that. And then the trick here is that doing that should not be computationally so expensive first. Then it shouldn't really destroy so much that computational graph, because this is the computational graph that you are working on. So as long as it's somehow compatible with that, so essentially finding those gradients would go through the same pipeline as our original neural network, then we are fine. So why not? And that actually magically works. Makes the optimization problem much faster, the solution much faster here. So it says consider a mini batch size of nj, which are these zj, the outputs. Well, the inputs to this layer, the output to the next layer, that should be zj minus 1. Yep, that should be zj minus. Well, no, actually that's the output. So what you can do is that instead of saying that, okay, let's try to normalize the inputs, we can as well say, let's try to normalize the outputs of one layer to be fed to the next layer, so inputs of the next layer. So this is the output of one layer, j, and this is sample I, so the output for that specific sample for some mini batch that you want to find the gradient with respect to that. Compute the batch mean and batch standard deviation. Very easy that you can do that, and then just normalize that. Okay, normalizing by these two bias term that you have seen, for example, in Adam. These are similar to that. Well, that's for different purpose anyway. But this is a normalization that you can do. And the new output, now add two more parameters to that computational graph. What is those two parameters is this gamma j and beta j for layer j. So what they do is scale this norm, this normalized outputs, scale them with gamma and add some b. So now you can imagine that really we don't need any bias anymore, because whatever the role of that bias is, it just biased to the all points, so that beta j can do that. But it just doesn't matter. Even if you add bias, then you can use the same computational graph. So here you can imagine that after this zj, we're going to have something more here, perhaps. You're going to need two additional parameters and then the same computational graph, finding the gradients, optimizing exactly the same thing. So from optimization perspective, the whole pipeline would be almost the same. But then now we train these two for every layer. So if you have capital J layers, then it's like two capital J additional parameters with almost nothing, compared to 60 million parameters for all those weights, okay? But then it works magically fine. I suggest you to read one references, which is this guy here, that says why this actually works. So their interpretation is completely different from the interpretation of the main authors here, completely different. And they actually disagree with that interpretation, saying that that could be wrong in general. But then they're saying that adding this term and normalizing will smoothen the optimization landscape. So you are running the same optimization algorithm with the same alpha, for example. But now what happens is that that alpha could be big previously. So you can now choose bigger alpha, for example. Why? Because the optimization landscape is much smoother. So L is smaller, and 1 over L, which is your step size, is now bigger. So you can take bigger steps, and then you can converge faster. So this is the whole idea here. By increasing the smoothness of end layers, it really helps in finding faster the optimization, the solution. So that's about, do we need still this activation function, nonlinear function sigma? We have claimed that traditionally, yes, we did need that to increase the expressiveness power, but then adding all these nonlinearity, for example, one of them is dispatch normalization. This is definitely a nonlinear operation. So then we do have this nonlinearity. So it's actually not clear if we really need to have that sigma anyway or not. But it's there, and it works fine, and people are happy with that. So why changing that? So I guess that's underlying. Okay, that is the whole message here. But then some of those interpretations that people have on the importance of why this algorithm works, or why we do need this specific layer or this specific set of functionalities, they may not be correct. They are experimentally validated, of course, they are working. That's why that most of people are using them. But some of them are not really theoretically validated somehow, or the reason behind is not clear for some of those functions. And magically, sometimes it happens that in 2015, for example, people are saying about that, and then 2,000 citations, all of them saying the same idea and the same hypothesis, the same reason, and then 2018, some people are saying that whatever they said could be completely wrong. And then people are now just repeating whatever they are saying again, perhaps 2001, and then somebody else will say that, okay, whatever they said may not be even correct. Okay, so what's the message here? The message is try to have a theoretical look at why this algorithm works. Of course, you need to experimentally validate that, but then always think why that can work. And then in many cases, actually, you can use optimization backgrounds that you get from the course to see under which condition the iterations will converge faster. Is it the main reason behind having this algorithm, why this algorithm works or not? And if so, isn't it a better algorithm? because the whole idea is just to make that optimization smoother with respect to something. So isn't it any better way to do that? Or we should use this one, which is computationally very efficient, but may not smoothen directly. So that's a byproduct that happens to be the main reason behind why it works. Okay, cool. Just 2 more minutes, I guess, and then we can finish this. Well, more than 2 perhaps. So it's about learning and inference over networks. So whatever we have said mostly so far was about training, how to make training more efficient, how to run over, how to run and then make inference over some neural network. Perhaps in general, you can look at a neural network as a very complicated model that you're going to train. Complicated means tons of parameters that you need to train. And the optimization landscape is very crazingly non-convex, in some cases even non-smooth, and then you want to optimize that. So this is the hardness of that problem. But then this is not the only problem whenever you want to apply those learned models on reality or on some practice. So we have seen some models of those problems in lecture 5, 6, and 7, and the quantization, limited resources, blah, blah, blah. We have seen that. But then there are some other questions that one may ask, actually. So given a trained model, one trained model that you can actually download is AlexNet for classification tasks. And then this AlexNet has 62 million parameters trained. So you don't need really to train that. You can just download that and install in your object detection in your camera, for example, or in your cell phone. And then you have now 1,000 object detection classifier. Very good one, by the way. But then it has 62 million parameters and 240 megabytes of size. And then if you need for different tasks to have tons of these networks like that, then you may be out of space or computational power anyway. Is it efficient anyway or not? Just imagine that we have seen that this dropout here, randomly dropping, works well. So always have this assumption that there are a lot of over-parameterization in that network. So most of those weights are really unnecessary to be there anyway. You really don't care if you just want to apply that on a server where you don't have any limitation on the resource, but whenever you want to apply that on some reality, in some real application perhaps, in some of them you really need to push your boundaries and then really look at these 62 million parameters, see what is the optimal number perhaps, or a smaller number. Again, as I said, end devices may have lower precision. Some cameras, for example, they may work with 8 bits, and then these values are with 32 bits. So how we can reduce that, make them compatible. And then finally, we'll not go through that anyway. Here, I'm just addressing the very first item here, but then there are lots of other problems that I really suggest you to think about them, and some of them are listed here. But just for the sake of compression, so memory limitation and precision limitation, you may go with some solution, and some of them works really magically fine. So just to get your attention, AlexNet, as I have mentioned, it has 240 megabytes, and then you can compress that to something of the order of size 0.4, and the accuracy is almost the same. So you wouldn't really you really notice anything, you wouldn't. So almost same accuracy, that much accuracy. So it says a lot about the compression. This may not be feasible, but then this is feasible on almost all the applications. You can do that. You can implement that. So there are many different approaches from lossy compression techniques. So the assumption here is that you are given a trained model, and you want to compress that somehow. So the first one that you may say is that, okay, it's over-parameterized, so just drop some of those. This is a crazy algorithm anyway, so by no means optimal, but you can do that if you're experimentalist, okay? So the first thing that comes to your mind is the first intuition, so drop some of the weights and then train that pruned model, much now pruned model with much less number of parameters. This is the first thing that you can do. Again, by no means is optimal or the best way to do that, but you can do that. On top of that, you can just lower the precision from 32 bits to 8 bits using round off. Again, you can do that. Again, by no means optimal. And on top of that, you can do some techniques which is more interesting actually to me. That cluster weights. So you can observe that some of those weights that you're training, they are almost on the same scale. Then what you can do is that you can cluster them and then change the mapping. So the mapping is that instead of map them individually, you can map them. You can use actually something like Huffman coding here, where you can, for example, say that 1 represents all those vectors, and then you have some index to say this 1 represents weight of this guy and that guy and that weight and that weight and that weight, instead of having 2.6, and then 1 can represent 2.6 with 8-bit precision. So instead of saying that 2.6, 2.6, 2.6, 2.6, you can just say 1 and then put the indexes. So something like that. And then lots of them, for lots of those weights, they are almost on the same scale. So you can do that actually. And you can get a lot of compression. So you can do all of them and then have this huge number of compression actually. Again, 2017. So you can see that these are very, very recent problem and very recent solutions. Okay, this is a question for you. Think about that. Could be a better way to train actually the model, to make the model more robust to these compression techniques afterward. Okay, cool. Any question? And read this slide. These are some more challenges that you may need to have, and some references.